We're now starting our descent into Riemann integration theory. The nice thing about the Riemann integral is that it is intuitive. Moreover, it's relatively simple. And perhaps it's intuitive because it's simple. It's intuitive, it's simple, but it also works in most cases that are under consideration. So for most nice functions, the Riemann integral exists. And we'll define it later and show that for a reasonably large class of things, we can guarantee that the Riemann integral exists. The price to pay for this simplicity and adherence to our intuition is that there are certain technical things that you would like to carry out with an integral that you have a difficult time to do with the Riemann integral. So for example, sometimes you take a limit of functions, for example, a pointwise limit of functions. This happens a lot. So for example, say with a Taylor series, that's a limit of functions. Well, sometimes I want to take a limit of functions, and I want to know that the limit of the integrals is equal to the integral of the limits. However, with the Riemann integral, swapping that limit operator, that function limit operator, and the integral operator, or symbol, becomes a very tricky proposition. There are certain nice cases where it'll work out. So on the other hand, there's Lebesgue integration, which we will not cover in class because it's an advanced topic. And the main reason we can't cover it in class is it is a very technical. It requires of measure theory, and the other important thing is that it has some very non-intuitive behavior. Sometimes there are things that seem very natural to say, or that you would like to say, but it turns out technically they just are not true. And so you have to be somewhat careful. The main power that Lebesgue integration gives you is that you can integrate a really large class of functions. And in particular, anything that is Riemann integrable is Lebesgue integrable. But the other way is not true. There are many functions that are Lebesgue integrable, but not Riemann integrable. So in particular, you get a larger class of integrable functions. But the nice thing about developing all this theory is that now you can develop important tools for swapping lim and integral. That are much nicer than, say, in the Riemann integral case. In order to develop the Riemann integral, we just need a little bit of machinery first, and so we need some definitions. Let a and b be real numbers with a strictly less than b. So in particular, we have the interval a comma b, and it's a non-trivial interval. A partition of the interval AB is a finite indexed set. Denoted P, and having the elements x1, having elements x0, x1, x2, all the way up to xn minus 1, xn, where the first member x0 is actually equal to a. X0 equal to a always has to be strictly less than x1, less than x2, less than inductively xn minus 1, which is less than xn, which is equal to b. The length of the partition is just the number of endpoints minus 1. Of course, there will be n plus 1 points in P, and so the length of the partition is just n. Because often we just associate it with the intervals of each sequential pair of members of the partition. The norm of a partition P of AB is the quantity. We denote it by double vertical bar. P double vertical bar is equal to, we'll take the maximum over k equals 1 all the way up to n, the length of the partition, of the difference between xk and xk minus 1. And if we're viewing the partition as breaking up the interval AB into the intervals x0, x1, x1, x2, and so on and so forth, then this norm is simply the largest length of one of those subintervals. The norm provides us with a handy notion of how fine the partition is. In particular, we can somewhat order the partitions in terms of the notion of refinement. if P is a partition of AB and Q is another partition of A, B, satisfying xk is one of the points in Q if xk is one of the points in P. Then Q is said to be a refinement of P. Now notice that you have to be somewhat careful. So we have the index k in P, and we just ask that this point is some index member of Q. So for example, we might enumerate the elements of Q as y0, y1, all the way up to say ym instead of n. And in that case, this xk would have to be equal to some yj in the partition Q. It's also helpful to pin down what we mean by the union of two partitions. So if P, Q are partitions of A, B, then P union Q, which is going to be some Z0, Z1, all the way up to Z, L. Is the unique partition of AB such that xk is equal to zj for some j if xk is a member of the partition P and yk equals zj for possibly some other j, of course. These j's don't have to align, is what I'm saying. So one could just think of this as I'm going to take the union of the xk's and yk's from P and Q, but then of course I have to order them. And so you might think of this as I take the elements in P, I take the elements in Q, and then I kind of zipper them together in order to maintain the ordering structure. But that's ultimately what we mean by the union of two partitions, as opposed to two sets. So now we're in our position to define the first steps towards the Riemann integral. Again, we let a and b be real numbers. So that the interval AB is non-trivial. And we let P equal x0, x1, all the way up to xn be a partition of the interval AB. We're going to set delta x sub k to be equal to xk minus xk minus 1 for this partition. That is, this is the length of the interval xk minus 1 comma xk. And we're going to do this for k equals 1 up to n. So that it's well defined. Now we suppose that f from the interval AB into the real numbers is bounded. That is, for all x in AB, the absolute value of f of x is less than or equal to some capital M number. And in particular, that M can be used for any of those x's. The first thing we can do is we can define the upper Riemann sum of f over this partition. And it's going to be this quantity u of f p is equal to sum. I'm going to go k equals 1 all the way up to the length of partition n, m sub k, which is a number I'll need to define in just a second, of f, delta xk, where mk of f is defined to be the supremum over the interval xk minus 1 xk. In particular, the image under this, which is also written the supremum over x in xk minus 1 xk of f of x. In particular, we note that because of this bounded condition, this number will always exist for our function. It's just the supremum of some real set. So this number is always definable. We can always get our hands on it. Similarly, we can define the lower Riemann sum of f over p. as the number L, F, P. Again, we have a sum, but now we have a little m sub k of f, delta xk, and where, similarly, little mk of f is the infimum of the function over the interval xk minus 1. Now it's useful to make some remarks to get an understanding of what we're calculating and the behaviors of those quantities that we're calculating. First of all, and this is somewhat a side remark, but it's important because we're taking sums. We note that if g is some function from the natural numbers into the real numbers, then we have that the sum from k equals m to the index n of g of k plus 1 minus g of k this sum is going to be equal to the quantity g of n plus 1. And then I notice that because I have say when I set k is equal to n, I'm going to have n plus 1 minus n, and then as I go down an index, I'll have g of n, which will cancel with the minus g of n from the k equals n part, and then I'll have an n minus 1. And that inductively cancels until you end up with just a g m. And this property of the sum is called telescoping. You've seen this property in calculus, and it's one of the nice ways that we can show certain limits of a series. If f from a to b into r, or again we're assuming a non-trivial interval ab, is f of x equals alpha for all x in ab, that is, I have a constant function, then for any partition P of AB, we have that U of FP is equal to L of FP is equal to just alpha times B minus A. And that immediately follows by telescoping. And thus it's not too surprising, since these numbers happen to coincide, it's not too surprising to say that the integral of this quantity is just alpha times B minus A. Now, the way we've defined things, it is trivial to establish that for any f from AB into R and P a partition of AB, the lower Riemann sum with respect to this partition is less than or equal to the upper Riemann sum of this partition. And that's easy to see because in that sum, this involves the minima over those intervals, and this involves multiplication by the maximum. Additionally, if Q is a refinement of P, then the interesting thing is that the lower Riemann sum will get larger. And of course, we've seen that this will be less than or equal to the upper with respect to Q. But the upper Riemann sum, right, because we're now taking a max over smaller intervals, will actually be smaller. So in some sense, as I increase this refinement and I get a finer and finer thing, I have this sequence that is monotonically decreasing, and I have another sequence that is monotonically increasing. And so we believe that somewhere it's possible that these two things could meet up. Another interesting thing is that if P and Q are any partitions of AB, we have to have that the lower sum with respect to P is bounded by the upper sum with respect to Q. And one way to kind of think about this is that any way that we put together a lower sum, we can think of as approximating by step functions or constant functions on our partition intervals. And so these are going to be the minimal value over those intervals. And in particular, those minimal values will always be under the function f. So the function f somehow dominates this constant approximation here, whereas any maximum approximation in terms of those constant steps on the intervals will be above f. Again, let a and b be real numbers with a less than b. And we define a function a, b into R. We say that f is Riemann integrable and really, when we understand that we're just talking about Riemann integration, we just say integrable on a, b if and only if f is bounded on AB, and for every epsilon greater than 0, there exists a partition such that the upper partition minus the lower Riemann sum with respect to the partition is less than epsilon. Now I know this quantity is of course greater than or equal to 0, but the fact that I can always get smaller and smaller error between these two terms means that I can establish a sequence of partitions in particular such that these limits, or the limits of the sums, will coincide. And therefore I can say that that quantity should be my Riemann integral. So this is the definition, but now we need to know that we have a lot of functions that we can integrate. In particular, we have the following theorem. If f from a, b into R is continuous on AB, then f is integrable on AB. Now we've shown that if f is continuous on AB, since A and B are closed and bounded, then we have that f is actually uniformly continuous. That is, whenever I fix an epsilon, I can find a delta to rule all of that is, given an epsilon, I can find a delta such that thus let epsilon be greater than 0, and note that epsilon over b minus a is therefore greater than 0. Then there is a delta greater than 0 such that x and y in AB and x minus y absolute value being less than delta implies f of x minus f of y is less than epsilon over b minus a. Now in particular, it's not too difficult to see that I can always find a partition that has a norm smaller than delta. That is, the lengths of the subintervals are less than delta. And that's easily accomplished by simply thinking about the Archimedean property, for example. So let P be a partition of AB with norm P less than delta. And note that xk minus xk minus 1 in this case will be less than delta for all k equal 1 up to n, where p is equal to x0, x1, all the way up to xn. By the extreme value theorem, since f is continuous on AB, f is also continuous on xk minus 1 xk, and therefore there are alpha k, beta k in the interval xk minus 1 xk with f of alpha k equal to the max of f over that interval, and f evaluated at beta k equal to the minimum of f over that interval. Now, since alpha k and beta k are in this interval, then their difference has to be certainly less than the difference between the two endpoints. So we note that beta k minus alpha k is less than delta. Then when we evaluate the upper Riemann sum less the lower Riemann sum, this is going to be equal to the sum, and of course merging these sums will have, via the distributive property, mkf minus little mkf delta xk. In particular, this is going to be f evaluated at alpha k minus f evaluated at that beta k. In particular, the maximum of f minus the minimum of f over an interval is always strictly positive, or non-negative rather. and therefore this is the absolute value, and since we have the absolute value of f evaluated at something at 2 points, the difference between the function evaluated at 2 points that are within delta of each other, our uniform continuity ensures that all these inner summands are a product of something that's less than alpha over b minus a, that was our epsilon greater than 0, times delta xk. But of course, that's a constant, so now I just have epsilon b minus a sum over k equals 1 to n of delta xk's. But delta xk's are going to telescope. And so ultimately this will be equal to epsilon over b minus a, and it'll telescope to be xn minus x naught, which is b minus a, which is therefore epsilon. Thus, we've found a partition P such that the difference between the upper Riemann sum and the lower Riemann sum on those partitions is epsilon, which completes the proof. The next thing we'll give is a somewhat pathological example of something that is not Riemann integrable. We define the Dirichlet function f of x is going to be equal to, I make a decision, it's going to be 1 if x is a rational number, and 0 if x is not rational. We claim that f is not Riemann integrable on the interval 0, 1. And the reason is this. We're going to justify that for any partition P of AB, U, that is the upper Riemann sum, will always have to be 1. And the lower will always have to be 0. Now why is this? Well, if xk minus 1, xk, for example, is a subinterval of 0, 1, then by density of the rationals, I know that there is a Q such that Q is in that interval. So those maximums will always be equal to 1. And so ultimately the sum will telescope and will evaluate the upper partition to be 1. Now the lower Riemann sum on the partition In particular, we also have a density of irrationals. And so, by the density of irrationals, we're going to have some irrational number in that interval as well, and hence the little nk f's will always have to be equal to 0. And therefore, because this is always 1, this is always 0, there's no possible way to choose a partition so that they're within epsilon of each other. And this completes the claim. On the other hand, this is Lebesgue integrable. And that is kind of the nice thing. And when you take the Lebesgue integration of this f, you'll actually get 0 out. It turns out that the rationals are not very important with respect to the Lebesgue integral. So the value on, say, a countable number of points is immaterial to the actual value of the integral when you're doing Lebesgue integration. Now there's yet another way to get at the integral that is relatively equivalent. Now we started with this comparison characterization of Riemann integration, but you could just as well define what's called an upper and lower integral. So let a, b be real numbers with a less than b, and suppose f a, b into r is a bounded function. The upper integral, so now I'm not taking a Riemann sum, I'm saying an integral of f on a, b is, well, I simply write u of f. So now notice this is free of any partition, and the reason it's free of any partition is that I set it equal to the infimum over the set of upper Riemann sums over the set of all partitions of AB. Now this is just a set of real numbers, and in particular it's bounded because f is bounded. And it's bounded below by any L of P, LFP, and therefore I know it's bounded below, and so it has to have an infimum. Similarly, the lower integral of f on AB is L of f equals supremum over the lower Riemann sums. And finally, if UF equals LF, then we define the integral of f by, and in particular with respect to the interval a, b. And we just write this symbol. We write this symbol, and it will be equal to the mutual value of UF and LF. Now we can remark that, of course, this upper and lower integral always exist, but it's not generally the case that UF and LF will be equal to each other. So for our Dirichlet function, this will always be 1 and this will be 0, and therefore we know that we can't write down this quantity and have it make sense. But here's a nice theorem that we can state. So again, non-trivial interval, f, a, b, into r, bounded. Then f is Riemann integrable if and only if U of f is equal to L of f. And this ultimately means that we could basically say that these are exactly the same definition. We could have started with this definition of the integral. So now if, we'll start with if f is Riemann integrable, then for each epsilon greater than 0, of course, there is a partition P of AB with the upper Riemann sum on this partition minus the lower Riemann sum on this partition being less than epsilon. Or we'll have that U of f, because it's an infimum, will always be less than or equal to UFP, will be less than or equal to LFP plus epsilon, which will be less than or equal to L of f plus epsilon. Well, since this holds, right, I can always find this partition that'll do this, and so that means that this holds for all epsilon greater than 0. U of f must be less than or equal to L of f. Now it's pretty clear that since each of my UFPs will be a bound for LFP, that L of f is also less than or equal to UF. We then must have L of f is equal to u of f. So that's the first part of the proof. In the next part of the proof, we assume this equality. Let epsilon be greater than 0 be given, and choose partitions P and Q of A, B with of course u of f being less than or equal to u of p is less than u of f plus epsilon over 2. And we can do this by the approximation property of infimums, and L of f minus epsilon over 2 less than L of q less than or equal to L of f. Then note that u of f evaluated on the union of these partitions, so it's a mutual refinement in particular of P and Q, minus L f also on the refinement, well, because of the refinement, I can go to the coarser partitions and still retain this upper bound. And now I know bounds on these quantities, and so this will be less than or equal to, or strictly less than, u of f plus epsilon over 2 minus L of f, again plus epsilon over 2, because the negatives will cancel. But of course I've assumed that u of f and L of f coincide, and so this is just equal to epsilon. And therefore we've found a partition such that the upper Riemann sum minus the lower Riemann sum on that partition is less than epsilon, and therefore I've shown that I'm also Riemann integrable, which completes the proof.